to this first, the first lecture in the series of Ramanujan Explained. Okay, I just wanted to show you what, just share with you before beginning on what I plan to do in the series of lectures. So the main objective is to go through various works of Ramanujan. The key references are these books. You can see here is Ramanujan's notebooks. There are 5 such volumes, and this one has 500 pages. And then there are 5 more volumes of this kind, which is Ramanujan's Lost Notebook. Another 5, this is close to 400 some pages. This is 430 pages. And this one is a special copy because I don't know if you can see. Can you see, if you can see my screen, if you can see my video, it's an autographed copy by the authors. So what I want to do is I want to, read through these books and explain various identities as well as I could understand them. And, it should be at a level which is, let's say, of math, which you can cover in an undergrad. So if there is something which is not usually covered in undergrad, I might repeat it here for you. So just be patient about that. And otherwise, if you feel that there's something which you want to learn something in background, I'll include it. So you can ask me to do that. So these are the Rogers-Ramanujan identities. First of all, this is the objective of our session today. And today's session should give you an idea of what all are the kind of things that we would do. It's kind of like a sample lecture, but we'll get serious from next time and do more and more identities. So these are 2 identities. There's a parameter Q. So you see 1 Q, Q raised to 4, Q raised to 9. So that pattern is easy. On the left, there's a sum. You're dividing by 1 minus Q, and then 1 minus Q square, and so on. So there's a pattern here. On the right-hand side, there are infinite products. So 1 over 1 minus Q, 1 minus Q raised to 6, 1 minus Q raised to 11, 16. Again, pattern is easy. It's 1, 6, 11, 16. So, every 5th number here. And then 4, 9, 14. So again, every 5th number. So it's a 4 or 1 mod 5, both these numbers in the denominator, and you get all of them. And similarly here, there is a similar kind of pattern. On the right, it's easier to see. It's 2, 5, 2, 7, 12. So it's 2 and 3 mod 5. On the left, it's k square plus k. So again, the denominators, you have 1 minus Q, 1 minus Q square, and so on. So speaking about these, Hardy said, it would be difficult to find more beautiful formulae than the Rogers-Ramanujan identity. So these have a long history. First of all, Ramanujan sent them in a letter to Hardy, and then for a while nobody could prove them. And then they found that they had been proved by Rogers 20 years ago. And then several proofs followed, and now there are hundreds of proofs which we won't get into. But today's objective is how one could discover such identities. So first of all, what you make sense of these identities. So I'll be writing on the screen. So please tell me if there's something not clear. Okay, so how do you make sense of such identities? So you have things like this. So you have k going from 0 to infinity, q raised to k square, 1 minus q raised to k. This is on one side, and on the product side, you have k going from 0 to infinity, 1 over 1 minus q raised to 5k plus 1, and 1 minus q raised to 5k plus 4. Right. So So how does one make sense of something like this? So how do we make sense of this? How do we make sense of this? There are two ways essentially. One way is to look at them as formal power series in Q, and the other way is uh, as analytic identity. So both are useful. We will cover both of them. But so this is more algebraic. So this could be method one, and this is method two. So this is the one which we will focus on today. Both are useful, um, and we'll get to as analytic identities at some point. But today, let's just look at formal power series. So what are formal power series? So if you just so this is a symbol for formal power series. This is the complex numbers. These are defined to be the set of all series of this type. So where AK belongs to complex numbers. And Q is like X. I mean, these are like infinite polynomials. This is series, the formal. And you can define a plus on them. So first of all, AK Q raised per K is equal to BK Q raised per K if and only if AK is equal to BK for all K. So coefficient wise, they should match, then they're okay. You can define a plus here. So you can say AK Q raised per K plus BK Q raised per K is defined to be AK plus BK Q raised per K. So again, K is going from 0 to infinity. K is going from 0 to infinity. K is going so usual properties of sums hold. So it's associative, it's commutative, etc. There's a zero, and there are additive inverse. So zero is just 0 plus 0 plus 0 plus q plus 0q plus 0 times q square, etc. You can multiply two of them. So before multiplying, maybe you can multiply. So let's see. So AK Q raised per K times BK Q raised per K is defined to be CK Q raised per K. K going from 0 to infinity. Again, 0 to infinity. And what is CK? CK is AK B0 plus AK minus 1 B1. So A0 BK. So this is the familiar Cauchy product. And again, we can have associative laws and commutative. There's a unity. So here there is a 1. And there's some kind of a ring structure. Third thing is that you can have a scalar multiplication. So this is defined to be C times AK. This is scalar multiplication. So what one is saying is that this is a vector space plus a ring, and it's usually called an algorithm. So what about invertible elements? So there are some invertible elements. So you can do inverses. So you can do inverses of some elements. So the key idea is, so first let us consider we use the so So for inverses, we use this idea. We use geometric sums. So what are geometric sums? So 1 minus q raised to minus 1 is usually written like this, and we can write it as 1 plus q plus q squared. So this can be proved this will be proved very easily in formal power series. So this is a formal power series proof. If you multiply these two guys, do you get 1 plus 0q plus 0q squared plus 1? So just on the left hand side, you can just say what is the coefficient of q raised to 0, the constant term, and it's 1 times 1, so it's 1 times 1, which is equal to 1. So this matches. This guy matches. Then coefficient of q. So you have this term q multiplying with this one, so it's minus 1. And this q multiplying with this one, so you get 0. And similarly, q raised to square, the coefficient is, so what are you doing? You're doing q squared. To get q squared, you multiply this by this, and you multiply this by this. So once again, it's minus 1 plus 1, which is 0, and so on. So you can see that the coefficient of q over s per n is 0. And this matches on both sides. So this matches, these all match the right hand side. So that finishes this proof. So just a simple, let's say, telescoping argument, but this sort of indicates what one does in formal power series. What one does is we compare coefficients. That's it. If some calculation is finite, coefficient wise, then it's fine. Now let's say in general, suppose I have a f q such that f0 is not 0. That means fq, so it's 1 over fq is 1 over a0 plus a1q plus so on. And a0 is not 0. If that happens, then I could take out the a0 here, and I'll get 1 over 1 plus well, 1 minus, I'll do 2 minuses, so minus a. Minus a1 over a0 and minus q maybe. So I'm taking this common, and then I have a minus q over, and there's a a0 here, so you get a over a0 here. And then you have a1 plus a2q plus so on. And this you can write it using the geometric sum formally as this 1 plus this guy q minus q over a0, a1 plus a2q plus so on, plus minus q over a0 square, a1 plus a2q plus square. Right, and so on. And again, in principle, you can calculate coefficients of q here is just one guy, then coefficient of q squared comes from this plus one of these guys, and so on. So every calculation to calculate coefficients of q raised per n is quite easy, is doable, and a finite process for any n. So you can divide. So f of q inverse exists in formal power series. provided f of 0 is not 0. Otherwise, you take out the q and maybe you get some low series or something like that. Okay, so this is how one has to interpret. Coming back to okay, so coming okay. Yeah, coming back to the Rogers-Ramanujan identities, we had q raised per k square 1 minus q square up till 1 minus q raised per k. So if you look at each term for every k, there's a q k square, and then this guy 1 over 1 minus q you can write as 1 plus q square and so on. Then 1 over 1 minus q square you can write as 1 plus q square plus q raised per 4 plus so on and so on for every guy. 1 plus q raised per k plus q raised per 2k plus. You can see that in principle you can calculate. So in principle you can calculate q raised per n for any n. And similarly, this product over here, that's much easier. So this product, 1 minus q raised per 5k plus 1, 1 minus q raised per 5k plus 4. Again, each of these guys you can write as 1 plus q raised per whatever. So this is 1 over 1 minus q, 1 minus q 6, and so on. K 0 to infinity. Times 1 minus q raised to the power 4 times this one. Each of these guys you can write as 1 plus q squared plus blah blah blah. So again, both sides can be interpreted as formal power series. And what we do is, what I'll suggest we all do is we will use Sage. So it's available at sagemath.org, and you can download it or you can use it online, but downloading is possibly better, easier to work, provided you have a Mac or a but if you have a Windows machine, it's a little bit cumbersome to install it. But you can use it online. And what I'll do is I will give some exercises. I'll give some exercises to get started in Sage. And a lot of formal power series calculations. So we can do some of them by hand, but formal power series calculations can be done on Sage. So we can compare the powers using Sage, so that we get a sense of what these identities are doing. So again, there are lots and lots and lots of identities. So it's helpful to do a few calculations by hand, but largely we'll be doing in Sage. Okay, so that's how one can interpret the thing, and the Rogers-Ramanujan identities. I'm just picking on one guy right now, but how the topic is, how did Ramanujan discover these identities? So for that we need to do a simpler we need to consider a simpler thing. We consider a continuous fraction. That's the simplest continuous fraction. This I hope many people have seen. So it's this guy. So what's a continued fraction? I mean, it's like a fraction which keeps going on and on. And the way one studies it is we chop it off. So we chop off at various places. At so chop off at 1, we get 1. Then we get 1 plus 1 over 1. Chop off here, and we get 2. Then we get 1 more. So now you notice this part is already calculated, right? So we have 1 plus 1 over 2. So that's 3 by 2. Then 1 more. Again, this part is 1 plus 1 over 1. 1 over 1 plus 1. This part is already calculated. 1 plus 1 over 1 over 1 plus 1. This part is 1 plus 1 over 3 by 2, which is 1 plus 2 by 3, which is 5 by 3, and so on. So well, this suggests how one can do it. So suppose we chop it off at Wn, then Wn is 1 over 1 plus Wn minus 1. So at the nth place we do this. And the other thing that you notice is that these numbers keep coming. So this number right here, this number comes in the denominator, this number comes in the denominator here, and if you keep taking numbers, you'll see that each numerator comes in the next denominator. So what we do is we substitute Wn equal to some new number, Fn over Fn minus 1, and then this guy gives Fn over Fn minus 1 equal to 1 plus 1 over Fn minus 1 over Fn minus 2, which implies that Fn equal to Fn minus 1 plus Fn minus 2. So it gives a recurrence relation. So this is called a 3-term recurrence relation. So this is very familiar. I don't know. So we begin, let's say F0 is 1, F1 is 1, then the next guy is 2, then some of previous 2 guys, 5, then 8, then 13, 21. So, does anybody recognize this? So these are what are called the Fibonacci numbers. So feel free to interact. Okay, so brilliant. So we figured out a formula for this recurrence relation for this continued fraction, and we can see it's Fn over Fn minus 1. We can calculate it like this. This is much easier to implement in a computer to calculate, and we can get an idea about what this function is. So what did Ramanujan? So what did Ramanujan? Okay, so this is a very very simple continued fraction, and what Ramanujan did was as follows. So he generalized 1 over 1 plus 1 over 1 plus so on to 1 over q plus 1 plus q squared, 1 plus q cubed, 1 plus q fourth, and so on. So he just added some q's, and let me say this is also something which is very natural. So these are called q analogs, and they're very natural things to do. So the simplest q analog, perhaps I should mention, simplest q analog is 1 plus 1 plus 1 is n. This is 1 minus q raised to power n over n. This is the geometric sum, right? So this is very well known. This is the geometric sum. Right. So let's calculate this. So let's call this I don't know something. Well, we'll just calculate it. So chop it off. So you get 1, then you get 1 plus q, then you get 1 plus q over 1 plus q square, right? So you'll get something 1 plus q square over 1 plus q square. Then you do 1 plus q over 1 plus q square over 1 plus q cube. So we would like to use this chap right here and use it here, but things are not matching up quite. So there's an extra power of q here and from here, right? So what we did in the previous case, we were trying to use the previous guy, right, in the Fibonacci case. So here it's not possible. So what we can do is we can start with something slightly more general. So let's call it CZ. And instead of this, I just add a particular Z over here. So I add an extra guy, extra parameter, 1 plus. And now C of Z is equal to 1 plus Q over C of ZQ. So our original guy, which Ramanujan would have just added the Q's, and then you just add a Z there, because we want to use this same trick which we used in for the Fibonacci now, right? So this is quite natural to do so. And again, some more experimentation. So some further experimentation. Very similar to the previous case. So some more experimentation suggests that let me substitute h of z over h of z. So instead of f, we have z and some slight this thing. And if we substitute it in this guy, right here, we'll get h of z over h of zq equal to 1 plus q times h of z. So this is zq square over h of zq. And this means that h of z is equal to h of zq plus q times h of zq. Right, so this is a more linear form. Again, we want an expression for h, so we assume now. So there is an inspired choice, and this is also something we do in math all the time. We assume that the solution is some kind of power series. So assume that h of z is summation of this form, a k z raised per k. So formal power series still. In z now, assume this and plug it in here. So what do we get? We get summation a k z raised per k, k going from 0 to infinity. Replace z by zq. So it's a k q raised per k z raised per k, k going from 0 to infinity, plus q times q square. So there is something wrong here. Did I forget a z? Yeah, there's a qz here. Sorry, this z I forgot. So there's a qz and then zq square. So it's qz. Then here we get ak q raised per 2k z raised per k, k going from 0 to right, and now we compare coefficients of z raised per k. So compare coefficients. Of z raised per k, and we get ak is equal to ak q raised per k. So so here there is an extra z, so it's zk plus 1. So you will get ak minus 1, and there's a q here, so it's 2k minus 2 and plus 1 here. right? And this will mean that, right, so this is 2k minus 1. So this implies that ak 1 minus q raised per k equals ak minus 1 q raised per 2k minus 1. So very good. Let's go on to the next page. So this guy, I'll just rewrite it. Pasting. Let's just rewrite it. Oh, there it is. Paste. Okay, so AK is equal to AK minus 1 q raised per 2k minus 1 over 1 minus q raised per k. We can iterate this, so it's AK minus 2 q raised per 2k minus 1 plus 2k minus, so 1 less, k minus 1, 1 minus q raised per k, 1 minus q raised per k minus 1. And you keep doing this till you reach A0, and you get 1 plus 3 plus 5 up to 2k minus 1. Here you get 1 minus q, 1 minus q square, 1 minus q raised per k. So just notice that, it's k minus 1 here, so it's k here. So it's A0, so you get 1 minus q over here. And the connection here, k and 2k minus 1. So when k is 1, you will get 2 times 1 minus 1, which is 1. Right, and this is easy to see that the sum of the odd numbers is k squared. So brilliant. What we get is, let me just write it on this side. What we got was h of z. So we got h of z. This A0, q raised per k square, and 1 minus q, 1 minus q raised per k. K going to be. So we can take z raised per k. And what we had was, so we can take, first of all, let's take. I mean, looking at the original, the first continued fraction, but this anyway will cancel. But what we were really interested in was h of, so our CZ, what was our CZ? This was h of z over h of z. So what it is k equal to 0 to infinity, q raised per k square, c raised per k, or rather the original one. Let me write the original one. Originally, we didn't have a z. So originally, we had c of 1 when z is 1. And this would be h of 1 over h of q. So h of zq with z equal to 1. And this will give you this sum, k going from 0 to infinity, q raised per k square, 1 minus q of the 1 minus q raised per k divided by. So z is q, so q square, k square plus k, 1 minus q. So this is the sum side. This is the sum side of Rogers-Ramanujan 1. And this is the sum side of Rogers-Ramanujan. So there they are. So this is how we discover. I mean, this is very natural. I mean, this could have been done by Ramanujan And it's very natural. And let me go back and say that, okay, we just start with this continued fraction, the simplest one. Then add a q, we need to add a z. Once we add a z, we think, can we get a power series solution? And if we can get a power series solution, that's what we get. We get a ratio of two power series. Right. So okay. I mean, this is not so tough. And let me just mention that this is the work of Dick Askey, who showed. So Askey suggested Ramanujan that got it this. The sum side. Now, what about the product side? So that's another trick. Let me just do the product. So let's see how to discover the product side. See how am I doing on time? I think. Doing okay. So here is the thing. So here is a trick which we so what's the trick? So recall the proof of geometric sum. This was the simplest Q analog. So let's say S is 1 plus Q square up till Q raised power n minus 1. So if I multiply by 1 minus Q, then I'll get 1 minus Q plus Q times 1 minus Q plus so on up till Q raised power n minus 1, 1 minus Q. So this 1 minus Q plus Q, and then there are higher powers of Q. So this is the critical one. This is the critical one. And this gets cancelled, so you get 1 plus higher power. Right. So the moral of this trick is that if you have S equal to 1 plus Q plus higher power, then multiply by 1 minus Q and you'll get 1 plus higher powers. Very simple observation. Right. So let's apply it here. Right. So let's just apply it on this guy. So we consider h of 1, which is 1 plus Q raised power 1 minus Q plus Q 4 raised power 1 minus Q 1 minus Q square plus Q raised power 9, right? Plus whatever. So this is of the form. So if I expand 1 over 1 minus Q as a power series, I will get 1 plus Q plus higher powers, right? So I get 1 plus Q plus higher powers. So I multiply both sides by 1 minus Q. So what do I get? I get 1 plus Q, right? So I get, sorry, 1 plus 1 times 1 minus Q plus Q here, plus I'll get Q raised power 4 over 1 minus Q square plus blah, blah, blah. And this guy will give me 1. This Q will cancel and I'll get 1 plus Q raised power 4, 1 minus Q square plus. So the next one I multiply is, so this is 1 plus Q raised power 4 plus higher power. So consider 1 minus Q raised power 4, and I'll get 1 minus Q raised power 4 plus, so here I'll get Q raised power 4. So 1 minus Q raised power 4, I'll multiply, I'll get 1 plus Q square. And here I will get the third term is Q raised power 9 over 1 minus Q had already cancelled, 1 plus Q square, and there's a 1 minus Q cubed plus whatever. So again, this is 1 plus q raised per 6 plus higher power. So next term I'll multiply is, what should I multiply by? I should multiply by 1 minus q raised per 6. And if I keep doing it infinitely, I can hope that, let's say, can hope that. So this, that I get 1. So, so brilliant. So this is, if you keep doing this, if you do this calculation a lot, you will get h1 times 1 minus q, 1 minus q to the 4, 1 minus q to the 6. And if you keep going on, you will get 1 minus q to the 9, then 11. And so so these terms, the powers are 1 and 4 mod 5. That means remainders of these powers are 1 and 4 when you divide by 5. So we can hope that h1 is equal to 1 over this guy. So somebody like Ramanujan would have calculated like hundreds of terms to make a guess and be almost certain that this is true. And this is actually a trick due to Euler. The trick due to Euler. Sure, I mean, surely it's an easy trick. Euler did it, and I'm sure probably Euler discovered it himself. So this gives the product side. Of Rogers-Ramanujan one, and as an exercise, you work out the details of the product side of RR2. And in fact, what I would like you to try is to do the same trick on this series. So S, let's assume S is some number right now, but this is a zeta function, so you can do it. So if you do the same trick, to discover Euler's product formula for the zeta function. So yeah, so great. We almost we figured out how exactly Ramanujan could potentially have discovered the Rogers-Ramanujan identities. I just want to show you what some notation. So some notation which will be useful later on. What we will this is called Q rising factorials. So when you open Ramanujan's notebooks, you see a lot of this notation. So we will need to at some point learn this. So this is equal to 1 if n is 0. Otherwise, it is 1 minus a, 1 minus aq, 1 minus aq to the n minus 1. So n terms for n bigger than 0. And we also see n equal to infinity case, in which case 1 minus aq to the k going from 0 to infinity. So as an analytical object, so as formal power series, no problem. As an analytical object, which we will need, we need this for convergence. So you usually convert, infinite products are not covered in undergrad. So we will cover at some point, so pending agenda, we will cover infinite products so that you become familiar with these. So in this terminology, Rogers-Ramanujan 1 you will see as this q q k, k going from 0 to infinity is equal to 1 over q raised power 5 infinity and q raised power 4 q raised power 5. And as analytical identities, you need q less than 1. And Rogers-Ramanujan 2, you will see like this. So if you Google Rogers-Ramanujan identities, you will see something like this. So, I mean, just mentally go through this. This is 1 minus q raised power 6, 1 minus q raised power uh, uh, 11, and so on. And this is 1 minus q raised power 4, 1 minus q raised power 9, and so on. And so each time when this q is replaced by q raised power 5, so the power of q changes, right? And this was already here. So let me conclude quickly by saying that what are our goals of these lecture series, and the goals may change slightly depending on requests from people who want to listen to these. So number one is to reorganize to some extent the uh, the work of the notebooks of Ramanujan. So this is the primary references are Burns, Ramanujan's notebooks, and Andrews plus Burns. This is a large task. So this is Ramanujan's notebooks and the lost notebook. So let me say that Ramanujan had some published work later, but the notebooks came before he went to England, and the lost notebook, typically most of it came after he came back from it. So that is the work which was not sort of available so much. So that work is actually perhaps more, there's a lot more to discover there than in the published papers. And what we want to do is we want to explain the identities and theorems, and if possible, find discovery approaches, how someone can discover such identities. So the hope is to, we don't know how Ramanujan thought, but the hope is to somehow get into that. We want to focus on techniques which you can potentially use. So for example, the Euler's approach to factorizing thing is a technique which has been very general, and we'll extend it, and Ramanujan knew it. We'll give an algorithm which you can use yourself to experiment with many series. So focus on techniques that work on many contexts. So in that way, it may be useful in your own work, and give background where needed. So here I'm more guided towards saying that it should be accessible to an undergrad, somebody who's studying undergrad. And definitely for a graduate student. So the target is to do things so that you can actually work in this area. So you get the basic things. I will give notes and I will give exercises. to learn so that you can learn the techniques. And gain familiarity. The results. So if they show up in your own work, that will be good. And all these will be placed on the website. You're free to write emails to me to make suggestions or to suggest if there are not too many people, then we can always figure out a way to check the exercise results. All right, so I just want to close now by showing you the identities again. And this particular talk was based on an article in Resonance, and it's available online and on my site. So this is it's on archive too, and it's available as a link. It's a published article in Resonance. It's a very good magazine, and I want to close by mentioning this comment by Hardy about Ramanujan, that he worked far more than a majority of modern mathematicians by induction from numerical examples. So this is some takeaway that we will find repeatedly coming in these lectures. Okay, so thank you very much and for coming, and please now you can ask any questions.